With all this talk in the previous video about things being acidic or basic or neutral, and with the talk in the next video about aqueous dissociations, I think it's important to talk about what happens when you have something dissociate or ionize itself, and you got to have a liquid to do that for the most part. And I want you to think ahead or think back, depending on the videos, to what we saw for acids and bases. For some generic acid HA, you can put it in water, and its aqueous dissociation equation gives you H3O plus and A minus. Okay, and then HA is donating a proton to become A minus, blah blah blah. That's an acid, and water ends up being a base. Over here, that's our conjugate acid and our conjugate base. All right, so in that situation, we've got water acting as a base. But if we look at some generic base aqueous dissociation where we have B, just some generic base, plus H2O, giving us BH plus and OH minus. We have B as our base. It accepts a proton to become BH plus, which means water is our acid here. And then this is correspondingly our conjugate acid and our conjugate base. So this is a situation we need to reconcile, the idea that H2O, depending on the circumstances, can be an acid or a base. And that is the idea behind something being amphoteric. So this idea of amphoteric is that they can act as either an acid or a base. So we have a species that may act as either an acid or a base. And the general idea for that, like if you needed to make up some expectations, if you have water, for instance, and it's around an acid, for instance, it'll act as a base. So it's generally contrarian, would be the English term. It goes against what it's around. So it acts as acids in the presence of bases, and we'll copy those words down, acts as a base in the presence of acids. And I'm sure someone out there is wanting to argue, but the idea is if you have a stronger base, then the amphoteric species will act as the acid. And if you have a stronger acid, then the amphoteric species will act as a base. So that's what we've got. Water is a situation where you can act as either an acid or a base. And if something is amphoteric and it can act as either an acid or a base, then it can potentially autoionize, especially if you have something like water that's a liquid. So let's look at that exact scenario. If we have H2O and H2O. Oops. In this particular case, we need something to be the acid and something to be the base, and I'll just claim that this is our acid and this is our base. Acids donate a proton, so bases accept. We'll have H3O plus as this gains a proton, and we'll have OH minus from the first species that lost a proton. Since this is water doing this, we have a special K term for this. It's not Ka, it's not Kb, it's Kw. And if you look here, pure substance, just in those other aqueous dissociation equations, so they're not going to show up. We're just going to have the concentration H3O plus times the concentration of OH minus. All right, this is a rather important equation in the big picture. I'll highlight it, and that looks horrible, so that's life. Because I'll rewrite it in Sharpie this time. Kw is our H3O plus and our OH minus. Good enough. So the Kw, the autoionization constant for water, changes with temperature because that's what K values do. Equilibrium shifts with temperature, and there's Le Chatelier explanations for that. And in this particular case, let's look at a few values that I pulled from, I don't know where, online, maybe like Chem Libre text or something where I steal everything else. At 0 degrees Celsius, Kw is 1.1 times 10 to the minus 15. Okay? At 25 degrees Celsius, which is essentially room temperature, kW is 1 times 10 to the minus 14th, and that's the number you'll see us use all the time. And maybe at 100 degrees Celsius, kW is 5.1 10 to the minus 13. This is changing. In fact, I would like to identify that change as we go in this direction. As temperature goes up, as temperature up, then our K value also increases, and there's some equilibrium significance of this. K increases. And then again, as we're talking about Le Chatelier relationships and all that, what this means essentially is that this autoionization is endothermic. And I'll sneak that off to the side. That means energy is required. So we'll write that. Therefore, this is endothermic. And that doesn't have to mean anything to you, but if you've watched some of the equilibrium videos, that's good for the big picture. When K goes up with temperature, essentially energy is acting as a reactant. Increasing that temperature shifts the equilibrium right, and the K value goes up. So this is endothermic. If you didn't care or need any of that information, just look at this, and then this is the one we're primarily going to be using. So what I want to tie this into right now, other than this idea of amphoteric species having the chance to autoionize, is our neutral and acidic and basic definitions. In a previous video, we had declared that to be neutral, in general, concentration of H3O plus had to equal the concentration of OH minus, right? And that's true at any temperature, right? And in general, Kw was H3O plus times OH minus. And that's at any temperature. So what we ended up with, or the way this works out, is at 25 degrees Celsius, concentration of H3O plus is going to be equal to the concentration of OH minus at 10 to the minus 7th molar. All right? And our Kw is going to be 10 to the minus 14th, and we saw that over there. Here's why it matters. One of the things we had written in the previous video about acid-base neutral is relating to pH, right? And so if you were to ask someone, what is a neutral pH, the answer is generally going to be 7, and there's a reason for that, right? If pH is the negative log of our concentration of H3O plus, and if at 25 degrees Celsius that concentration is 10 to the minus 7th, we end up with a pH of 7.00, all right? So at 25 degrees Celsius, this is neutral. But that changes at different temperature, and I think that's the part that most people don't know. Neutral being 7, a pH of 7 being neutral, is only true at 25 degrees Celsius. At different temperatures, it's different things. Those concentrations are going to change, and the neutral concentrations will change, but it'll still be neutral. Okay, so let's make a little room for that. And we'll look at these two scenarios here. So if Kw, so we'll say at 0 degrees Celsius, Kw is still going to be H3O plus and OH minus, right? But now for 0 degrees Celsius, it's going to be 1.1 times 10 to the minus 15th, okay? So our neutral is when concentration H3O plus is equal to concentration OH minus, right? And that's going to be the square root of Kw. And right here, when we do that, we get a 3.3 times 10 to the minus 8th molar. So at 0 degrees Celsius, 3.3 times 10 to the 8th molar is neutral, okay? At 25 degrees Celsius, 10 to the minus 7th is neutral, and that gives us a pH of 7 for neutral. So let's get our pH here real quickly. If pH is the negative log of concentration H3O plus, we end up with a pH there of 7.47 for neutral. That's a different number, yeah? So neutral can mean different things. At 25 degrees Celsius, 7 is a neutral pH. At 0 degrees Celsius, 7.4 is a neutral pH. That's not a basic solution, that's a neutral solution. It just is neutral at a different concentration because that K value has changed, right? Since K is changing, the neutral concentration is changing, but this is still equal to this right here. That was our KW right there. And we'll do the quick calculation for 100 degrees Celsius, which gives us this K of 5.1 times 10 to the minus 13. KW is always H3O plus times OH minus. And right now with 100 degrees Celsius, again, that's 5.1 times 10 to the minus 13. To be neutral, the concentration of H3O plus is going to have to be equal to the concentration of OH minus, and that's going to be the square root of KW, which is going to be, in this case, 7.1 times 10 to the minus 7. And to get our pH is the negative log of 7.1 times 10 to the minus 7, which in this case is 6.14. And that would, under circumstances of 25 degrees Celsius, what we're used to, you would think 6.14 is acidic. You would think that 7.47 is basic, but again, no. The definition of acidic and basic is still the same. More H's than OH's for acidic, more OH's than H's for basic. And in both of these situations, the number of H's and OH's are the same. It's just that the balance point, the equilibrium point, has changed based on that number right there. Neutral now is based on this concentration, which gives us that pH. All right, so that's the basic idea of pH and how K changes, KW changes with temperature, and it's a nice tie-in to equilibrium. And with this little bit of space I have left, I just want to mention another classic example of an amphoteric substance autoionizing, and that is ammonia. All right, so if you have NH3 and you put it with NH3, all right, and we'll go liquid on this. It turns out that one of these NH3s can donate a proton and one can accept, in which case we'll end up with NH4 plus and NH2 minus. And in this situation, it has autoionized, it ionizes itself, and that's a case with ammonia. All right, this super useful stuff in the big picture, this is the Bible of acid and base problems, KW being H3O plus times OH minus. And I think it's worth mentioning also right now, looking right here, which is H3O plus times OH minus is some number, which means that H3O plus never gets to be 0, OH minus never gets to be 0. If H3O plus goes up, if something becomes more acidic, then OH minus has to go down correspondingly, because it can't be 0. So a common misconception is that in an acidic solution you don't have any OHs. No. In an acidic solution you just have fewer OHs than H's. And in a basic solution, this number goes up and this number goes down. So in a basic solution, you have H3O pluses still, you just have fewer of them than hydroxides. All right. So once again, in slow-mo, neither of these ever get to be 0, but as one goes up, the other goes down, and that's what makes something acidic or basic. When this number is the same as this number, that's neutral. And the point at which things are neutral changes based on temperature, because K values change with temperature.